Hello, I'm Ryan Baker and this is Big Day in Education. Welcome to Bayesian knowledge tracing, a method for knowledge inference. Today we're going to talk about Bayesian knowledge tracing, which is the classic approach for measuring tightly defined skill in online learning. It was first proposed, along with a bunch of things, but in a paper by Richard Atkinson in the 60s, but it's most associated with, most thoroughly articulated and studied by Al Corbett and John Anderson.
So Bayesian knowledge tracing, BKT, it's been around a long time. Still, as of this recording in spring 2023, it's still the most widely used knowledge tracing algorithm used at scale. And that's because it's interpretable, its performance is very predictable, unlike some of the algorithms we're going to talk about later this week. And although its performance isn't as good as really any of the modern alternatives, it still achieves good enough performance for a lot of real-world tasks.
The key goal of BKT is to measure how well a student knows a specific skill or knowledge component at a specific time based on their past history of performance with that skill or KC. The skill should be tightly defined. Unlike approaches such as item response theory, which we'll discuss later this week, the goal is not to measure overall skill for a broadly defined construct, such as arithmetic, but to measure a specific skill or knowledge component, such as the addition of two-digit numbers where no carrying is needed. What's the typical use of BKT? It's to assess a student's knowledge of a skill or knowledge component X, based on a sequence of items that are dichotomously scored, which means that the student can get a 0 or a 1 on each item, nothing in between. It turns out actually that you can use BKT even for cases where there's partial credit, but it's not the most common use. And each item corresponds to a single skill. An item doesn't have to be like a separate problem. It could be a problem step in an overall problem that has a distinct skill associated with it. And the student can learn on each item due to help, feedback, scaffolding, whatever. The point is that as the student's practicing, they're also learning. This is not just a test, it's actually a learning system.
So what are some of the key assumptions of Bayesian knowledge tracing? First, it assumes, in its classical form, that each item must involve just a single latent trait or skill. This is different from PFA, which we'll talk about next lecture, and there's also extensions of BKT that get past this. Each skill has 4 parameters. I'll talk about those 4 parameters in a minute. Only the first attempt on each item matters, or in other words, is included in the calculations. From these parameters and the pattern of successes and failures the student has had on each relevant skill so far, we can compute the student's latent knowledge, P of ln. How probable is the student to know the skill they're currently working on? We can also compute the probability P-core that the learner will get the item correct. Another key assumption, a two-state learning model. Each skill is either learned, known, or unlearned, unknown. In problem solving, the student can learn a skill at each opportunity to apply that skill. And a student doesn't forget a skill once he or she knows it. Again, there are extensions of BKT that do allow for forgetting.
The model also makes some performance assumptions. First of all, if the student knows a skill, there's still some chance that the student's going to slip and make a mistake. But at the same time, if the student doesn't know a skill, there's still some chance the student's going to guess and get the correct answer. So there's a link between performance and learning, but it's not a perfect link. So let's look at the classical BKT model now. You can see the 2 states on the left, not learned, on the right, learned. The first parameter, PL0, is the probability that the student already knows the skill before their first opportunity to use it in problem solving. In other words, students don't come into our learning as a blank slate. They come in already having a certain probability of knowing what we want them to know. Second of all, P of T, the probability that the skill will be learned at each opportunity to use the skill. If our system promotes learning at all, students' performance should get better over time. They should actually learn. And P of T accounts for this. P of G, the probability the student will guess correctly if the skill is not known. So even if it's not learned, even if they haven't learned the skill, there's still a certain probability they'll get it right. And P of S, the probability that the student will slip and make a mistake even if the skill is known. Now notice that the probability of correct, given that you know it, is 1 minus P of S. In other words, if there's a 20% chance that you'll slip, then there's an 80% chance you'll get it right if you know it. How do we predict current student correctness? Well, P-core is simple. It's just the probability you know it, P of ln, times the probability you didn't slip, plus the probability you didn't know it, times the probability you guessed. In other words, there's only 2 ways you can get things correct in the world of Bayesian knowledge tracing. You know it and you don't slip, or you don't know it and you guess. In Bayesian knowledge tracing, whenever the student has an opportunity to use a skill, the probability that the student knows the skill is updated, using formulas derived from Bayes' theorem. The formulas are as follows. The probability that you knew it beforehand, given that you got it correct, is the probability that you knew it beforehand and didn't slip, over the probability you knew it and didn't slip, plus the probability that you didn't know it and you guessed. So it's basically the same as the probability of correctness, just moved around a little. Similarly, if you got it wrong, then how did you get it wrong? Well, you must have known it and slipped if you already knew it. So if you already knew it, then you previously knew it and you slipped, and the two possibilities are you previously knew it and you slipped, and you didn't know it and you didn't guess. Finally, once we know the probability that they knew it beforehand, given their correctness now, we can look at whether they learned it. So the probability that they know it at time n, given action n, so after the action, is the probability they knew it before the action, plus the probability they didn't know it before the action, times the probability that they learned it. So in other words, let's say there's a 30% chance you know it after the previous action, and there's a 10% chance you learn it. P of t is 10%. In that case, the probability you know it afterwards will be 0.3 plus 0.7, the probability you didn't know it, times 0.1 for 0.37. Let's look at an example a little more in depth. Let's say the probability they knew it beforehand is 0.4. The probability they learn it, if they don't know it, is 0.1. Probability of slip is 0.3, and the probability of guess is 0.2. In that case, the initial probability they know it before they do anything in the system is 0.4. P of L0 becomes P of Ln minus 1. Let's say they get it wrong. In that case, the probability they knew it beforehand is the probability they knew it beforehand without this information times the probability of slip, because they got it wrong, over that probability plus the probability that they didn't know it times the probability that they didn't guess it. So 0.6 times 0.8. The inverse of 0.4 is 0.6. The inverse of 0.2 is 0.8. So when we compute that out, we get 0.2. So before we knew they got it wrong, we thought they had a 40% chance of knowing it. But after they get it wrong, we have a 20% chance that they knew it. They still might have slipped. Then the probability that they know it afterwards is the probability that they know it plus the probability that they didn't know it times the probability they learned it. And that is 0.28. So now we move that down, and that becomes the probability they knew it before the second action. So let's say the student gets the action right. In that case, the probability that they knew it before they got it right is the probability that they had known it and hadn't slipped over that probability plus the probability they didn't know it and they guessed. That turns into 0.58. So you can see when they got it wrong, they went down from 0.4 to 0.2, which came up to 0.28, and then that 0.28 after they got it right was reassessed to be 0.58. These are pretty big changes, and that's because the probabilities of slip and guess are pretty low in this model. So then the probability that they knew it afterwards is the probability that they knew it beforehand plus the probability that they didn't know it times the probability they learned it, which comes out to 0.62. A few notes about BKT. First of all, BKT only uses the first problem attempt on each item. This throws out lots of information. I mean, if you think about it, a student gets something wrong, then they get it wrong again, and then they get it wrong again, then they get it wrong again, then they finally get it right, is different than if a student gets it wrong, and then 3 seconds later goes, oh, shoot, I did 2 instead of 3, and they get it right. So this throws out a lot of information. But on the other side, it uses the clearest information. Several variants to BKT break this assumption, at least in part, and we'll talk about that more later in the week. Typically, the potential values of BK parameters are constrained. I mentioned that the guess and slip we had are kind of low, and so the model is fairly dynamic. We do want to constrain those values somewhat to avoid what's called model degeneracy. Model degeneracy is based on violating the conceptual idea behind knowledge tracing. That conceptual idea is knowing a skill generally leads to correct performance, and correct performance implies that a student knows the relevant skill. If you can't trust these things, you're kind of in trouble. So hence, the idea is, by looking at whether a student's performance is correct, we can infer whether they know the skill. And again, if you can't trust that, you're in trouble. Essentially, a knowledge model is degenerate when it violates this idea. When knowing a skill leads to worse performance, and getting a skill wrong means that you know it. It's weird, right? That's why it's called a degenerate model. Some constraints have been proposed by different people. Joe Beck has proposed that the probability of guess plus the probability of slip has to be less than 1. Baker, Corbin, and Alavin have proposed that guess and slip each have to be less than 0.5. And Corbin and Anderson originally proposed, and this was not entirely just for model degeneracy, but also based on kind of theorizing about what was probable, that P of G has to be less than 0.3 and P of S has to be less than 0.1. Baker would say that when either guess or slip get above 0.5, you're in a situation where the behavior doesn't mean what it looks like. Beck would say that for some cases where the modeling can get difficult, specifically like with automated speech response where you're making inference, that there might be enough error that you might get guess or slip above 0.5. But as long as they're under 1.0 as a sum, it's still okay. Which one you trust is kind of a matter of opinion right now. I think that there's good arguments on both sides. So how do we know if a knowledge tracing model is any good, beyond whether it is degenerate or not? Well, our primary goal is to predict knowledge. But knowledge is a latent trait, as we've talked about. So instead, we check our knowledge predictions by checking how well the model predicts performance. In principle, any set of 4 parameters can be used by knowledge tracing. But parameters that predict student performance better are preferred. Obviously, if you've got one set of parameters that you can run, but it's terrible, and one that actually fits pretty well, hopefully you prefer the one that fits well. So we pick the knowledge tracing parameters that best predict performance. Defined as whether a student action is going to be correct or wrong at a given time when knowledge tracing predicts it will be. Now I could talk for an hour or more, many hours, talking about the ways to fit Bayesian knowledge tracing models. I'm a total geek for this,
If you don't want to get to the trouble of fitting it yourself, which probably isn't worth the trouble unless that's actually an area of interest for you, there are 3 public tools you can use. Probably the best one is HMM-SCLBL by Michael Udelson, but 2 other options are BNTSM, the BayesNet Toolkit Student Modeling, which does expectation maximization, and BKTBF, BKT Brute Force, which does a grid search algorithm. All 3 of these are open on the web, and you can use them.
Which one should you use? Obviously I'm biased because I helped write one, but they're all fine, really. They work approximately equally well. My group uses BKTBF to fit classical BKT, and BNTSM to fit the variant models, and I'll talk about those in a few lectures. But some of my commercial colleagues use FitBKT at scale, and they're pretty happy with it. They're all fine. The one thing you shouldn't do is to use the Excel equation solver. That replicably does worse for the problem than these packages. Not a good idea. Use some existing package, and they're out there. In your assignment, you'll have a chance to do that. I want to conclude by saying that there have been a bunch of extensions to BKT. It's not just a good model, it's also been the basis for a lot of other interesting work. We're going to discuss some of the most important ones in class later in the week.
One other important note. One cool thing about BKT that the modern alternatives don't have is that there's actually a way to determine how big a sample size you need for BKT. It turns out to depend both on the number of students you have and the number of practices per student. So it's not simply that you need a certain number of students, you also need to know how much data you have per student. And this isn't currently available for any other knowledge tracing algorithm that assesses knowledge as it changes. For details on this method, see Slater and Baker in Behavior Metrica in 2018.
So, thank you very much for coming today. Next up, we'll talk about one of BKT's rivals, performance factors analysis. Thank you very much.